Hello. Oh man, and welcome back. So in the last video, oh, hold on, my furnace is about to turn on. Let me go turn that off. Okay, I'm back. Sorry. Okay. It's so cold, but my furnace is so loud and it just is annoying to everybody. So I suffer for you all. I suffer for you all. Okay. Anyway, so in the last video, we were talking about p-values and t-values and how they're both kind of related. T-values represent a distance between two samples, and p-values represent sort of the probability that that difference is consistent across the whole population rather than just our sample. And we also talked about practical and statistical significance. Okay. And now we're going to be talking about that idea of significance here through the lens of hypothesis testing. And this idea of hypothesis testing is, it may be familiar to you, it may not be, and that's okay if it's not. But this is kind of the whole foundation of what we'll be doing in this class kind of from here on out. Not necessarily the same context every time, but definitely the same sort of idea where we have two we have two hypotheses, a null and an alternative hypothesis. Now, before I get into this idea here, let me go back to these figures and let me ask you a little question. Let's look at this one. Is this difference between these two samples, is that big enough for us to really care about? Probably not. It's rather small. Again, we're sort of being very vague here with the units and what these kind of represent. But as far as this difference is not that big. These two samples are pretty similar. And in the context of our example, where we are working with different types of fertilizer, or at least one type of fertilizer versus not using fertilizer, this might not be big enough for us to really care about. Okay, this difference in yield, we'll say. Okay, and so this t-value is not that large. This p-value is very large because they're related in that kind of way. This p-value might be too big for us to really care, at least care about in this instance. But here we see that p-value has grown. Well, not grown, it's shrunk. And the t-value up here has grown. The distance between these two samples is starting to kind of grow, right? They're becoming less similar, okay, in this kind of new instance here. And from kind of here on out, we're not going to be so much looking at the t-value. We know what it represents. It represents this distance. But what we care about in this class and in most statistical analysis is this idea of the p-value, the probability that this difference is true in the whole population. Now, based on this sample, this p-value might be small enough for us to say, okay, I care enough about it to say that maybe it is true. Okay, maybe that this difference is true. Okay, and then of course here in this last example, these two samples are really far apart, right? And this p-value, the probability that this difference is just due to randomness is very small. Okay. Now, this p-values can range from 0 to 1 because they represent a probability. What's sort of the threshold for us as far as statistical significance goes? What value are we okay with for saying that there is a difference, that probability is small enough for us to say that, we're okay with taking some % chance that we're wrong as far as claiming that there is a difference? Well, that's where we come here. We come full circle, kind of, back to hypothesis testing. Now, we have two hypotheses. If you've taken intro stats from me, I would have you write out, what the null hypothesis is and what the alternative hypothesis is. In this class, we're not going to be doing that so much because we care more or less about the practical sort of implications here, rather than being kind of tedious with writing out every single detail. Okay, so the null hypothesis for this class, usually in the world of t-tests, t-tools, is that there is no difference between the two samples that we have. There is no difference. And when we say that there is no difference, that the two samples are so similar that there's quite a bit of overlap, we usually make that claim when our p-value is greater than 0.05. And remember that p-values represent the probability that our difference is due to chance, okay? And anything that is over a 5% chance that it is due to randomness is no-go for us. We'll just go ahead and say that there is no difference between the two things, okay? And it's as simple as that. So if our p-value is greater than 0.05, we're going to trash it and say that whatever experiment we were doing didn't have an effect on the overall outcome, or at least the difference between, in our case, the experimental group and the control group was small, not big enough for us to really care. That p-value, the probability that difference we saw is due to chance is too big for us to say that it's going to be true across all of the hops in our farm or all of our population. Okay, and then on the other hand, alternatively, we have the alternative hypothesis, where whatever the difference between the true mean and the comparison is not zero. What we instead will say is that there is just some difference. Okay, and we will make that claim that there is some difference in the population when the p-value, you guessed it, is less than 0.05. Okay, so we're pretty much okay with anything smaller than a 5% chance due to randomness. Okay, due to randomness, just random chance. So anything less than 5% is good for us. Why 5%? Great question. The guy who did this, William Gossett, and a few others, when they were doing this without computers, doing everything by hand, they were doing calculus by hand, and that's just no fun. Takes a long time. They just said 5% is good, and we're going to do, essentially, we're going to rewrite that whole t-table with the p-values and everything by hand. They just wanted to do it for the single value, and it just kind of stuck. There really is no reason why we use a 5% chance due to randomness. It could be 0.1, could be 0.2. 5% is small. Some people prefer smaller. Some people want a 1% chance due to randomness, and that's okay too. That just means that we have to have something that looks more like this to say that there is a difference rather than something that looks like this, okay? Again, these totally conventional, these ideas here are totally conventional. You could do whatever you want. In our case, for this class, we're going to probably stick with 0.05 because there's a lot of things related to this 0.05 that make life a little bit easier. But there is some, some fields where this value can be smaller or larger. And then that's just when you change sort of the criteria for when you claim this, okay? So if your p-value is maybe, if you want to say, you want to go with a 0.1 instead of 0.05. So anything less than 0.1, you go with the the alternative hypothesis, that there is some difference, that the thing that you were testing had some effect, okay? Let me actually write this too. This value here, this is kind of conventionally known as alpha. So you have an alpha value of 0.05, and that's fixed. That's always there. Your p-value is the thing that changes, right? Your p-value is the thing that is calculated between, the difference between these two things in our case, okay? So you have an alpha of 0.05, and anything less than alpha, you go with the alternative hypothesis. Oh, man. Okay. So in the end, is there a difference? Yes or no? How do you know? It's based on that p-value there. Anything bigger than 0.05 or whatever your alpha is set to be, you say that there is no difference. It's not big enough for you to really care about. Anything less than 0.05, you say that that difference is big enough to care about, and you say that it is there. Okay. Okay. Now with that, we'll move on. Hold on. Let me see here. Yeah. Well, I'm going to stop the video, and then we'll move on to kind of the components of a t-test, and we'll just kind of go from there. Okay. See you in the next one.